We have a very special show today. We have, in addition to Ben Jordan, we have Ben Wolke. I'm pronouncing your name correctly this week, right?
Alan.
Except my first
Alan
name is
Wolke.
Ben.
Did I already do it? I tokenized. I'm sorry. Alan Wolke. So I was actually pronouncing your name last week as if it were Japanese. I was a k noise in there, but because I didn't know if it was silent E or long E, so I was
Well, it's long
kind of
E
cutting
for the American pronunciation, and it's the Wolke in the German pronunciation.
There you go. There you go. Yeah, so
for-
I was trying to go, I'm not just a typical Yank. I'm trying to realize the pronunciation. But
Right.
Alan is joining us from Tektronix, but also you're a long-term ham we were
Yes,
just
I am.
talking about. And you brought some cool stuff to show us today. And I don't want to interfere too long. Tell us about yourself, Alan. Tell us a little bit about your career and why we
Sure.
asked you to be here today.
Absolutely. So yeah. So again, I've actually known Ben for many years now through various channels
Bill.
here. But, so
You
well,
just
yeah,
did
I
it.
think I think I was a guest in the Dinosaur Den. It was like 5 or 6 years ago now. I think is
Yes.
how long ago that was. But,
Maybe even longer.
But yeah, so I started off my career in 1985 when I got out of college and served various roles in doing integrated circuit design, application support, test development, things like that, for everything ranging from fiber optics to hard disk drives to RF type circuits and things like that. And so, but for the last 15 years or so, I've been a field application engineer for Tektronix, which means I just get to have fun pushing buttons, twiddling knobs, and showing people how to use equipment and helping them to troubleshoot things and get involved in everything from radar and electronic warfare to commercial wireless applications to EMI and EMC problems and things like that. And all kinds of interesting, mixed signal applications where folks are embedding wireless interfaces into devices and trying to get them all to work correctly and all that type of thing. So lots of fun stuff. Getting to play with some of the best test equipment in the world. So and I don't have to go buy it all because I have to have it to support my customers. So
So cool.
and then being I've also been, as you mentioned, a ham radio operator since about 1980. So I've been doing that for 40 some odd years. So I've always had a little bit of an interest in RF, and it's always given me an excuse to have test and measurement equipment around the house, so as if I needed an excuse. But But so this is like the best job in the world as a ham, where I get to, support, some of the best RF test equipment in the world and have it accessible to me. And boy, I might use it for a ham radio application or two now and then. Who knows?
So we're getting complaints that the echo is so bad that it's hard to understand, and I'm asking if it's just me and Ben or if it's you. Can you, Alan, can you turn down your speakers to where it's almost hard to hear us?
Sure. Yeah.
So we're going to let you do most of the talking if you're not echoing.
Okay. I think that's that. I turned them down
somebody's
quite a bit.
saying
How's
it's
that?
getting better.
Okay.
All right, so continue. I didn't mean to interject, but Echo's a longtime protagonist of us here. Oh, actually, somebody's saying it was on their end. Okay, very good. So we're good.
Okay. Alrighty. So yeah, so like I said, so the ham radio end of things has kind of entered me into building a YouTube channel that has grown in popularity over the last decade or so. I've got a little over 330 videos up on my channel now. With
what's the name of your channel?
I'm sorry?
Where can people find your channel?
Oh, the YouTube channel name is just actually my call sign. It's right there, W2AEW. So youtube.com/W2AEW.
There's some really cool stuff
you
there.
take a look. I don't know if I'm on screen or not, but you can actually see it on the back of my shirt there.
There you go.
So, so I've got about 150,000 subscribers and close to 19 million views of the videos on the channel there.
Wow.
But the channel is primarily composed of test and measurement stuff, basic electronics, some really basic stuff like the relationship between voltage and current through inductors and capacitors, to all about diodes and things like that, to more advanced topics like digging into how a Gilbert cell multiplier works, or maybe doing a walkthrough of an RF transceiver, or doing some debug or troubleshooting or repair of a piece of equipment, to test and measurement topics, to other various ham radio activities and things like that. So it's a mix of all the things that I kind of have an interest in, at least from an electronic standpoint. I leave my car stuff, my woodworking stuff off the channel, but it's all kind of electronics, test and measurement, ham radios, basic electronics type stuff, with a lot of hand-drawn drawings, Forrest Mims
Which
style
work.
documents. And
Yeah,
things
no,
like
those
that.
totally work.
Mims. So
yeah. And you've hit all the basics of basic electronics. I would tell people, if you wonder how a diode works or something like that, before I would do a Hackaday video, I'd go check your video out. Just to get background and make sure I'm not to step in it myself. So it's a great channel.
Thank you.
So, wow, 19 million. That's
yeah. You should take some satisfaction knowing that probably most of the other electronics related channels are officially or unofficially referencing your work, and
Yeah.
what you've done for anyone who wants to learn electronics is really monumental, and it's a just massive contribution. And everyone owes you a gratitude for that. So.
Well, I appreciate that, because you got a lot of guys out there like Dave Jones with the EV blog channel, which is 10 times larger than my channel, and there's Big Clive and all these other guys that are out there that do this stuff too. So I don't set up a Patreon account on mine. I try to keep the fluff to a minimum. And it's all about the content and not about my personality, because I'm a ham. I don't have a personality. So, but, so I try to keep things just short and sweet, and just, a high density of content, in the video. So most of them are, 10 or 15 minutes long or less. And
it's exactly what we need. And I wish college textbooks could be written the same way.
Well, I also try to fill in the holes of what's not in the college textbooks, right? Because so many times you'll find that, there's very little practical information in a lot of the college textbooks. They don't teach you the difference between a tantalum cap and an aluminum electrolytic cap. They don't teach you the difference between, COG dielectric and an X7R, right? They don't teach you those things. And these are the kind of things that you don't learn till you get out in the field,
Yeah.
Or that a tantalum cap is more likely to blow up in your face the first time you turn it on compared to an aluminum electrolytic.
Yeah, the failure modes are quite different, and one is a lot more exciting than the other.
Exciting, yes, yeah. I still to this day put a piece of paper over a circuit I'm turning on for the first time, just because I've had tantalum caps in production go off like little matchsticks.
Yeah, letting the smoke out of something isn't as bad as letting the bang out of something. So.
Yeah. So I'm sorry, Ben, what were you saying?
I was just saying tantalums love to fail short.
Yeah.
Instead of open.
Yeah. Right.
Yeah.
So what are we looking at here on the screen? I mean, this is beautiful. I see some things I recognize and some other stuff that's. But what are we looking at?
So we're actually looking at a real-time spectrum analyzer. Okay. So what is a real-time spectrum analyzer? So it might make sense to talk about what just a spectrum analyzer is first.
Yes,
right?
please do.
So a spectrum analyzer is a piece of equipment that will show you the frequency content of a signal. So the two axes are, I don't know if you can kind of see the little blippy thing on my thing here.
I see.
The vertical axis is typically calibrated in power, and usually expressed in a logarithmic thing like in dBm, which is decibels relative to a milliwatt. And then the horizontal or x-axis is a frequency range. Okay, so you're showing how much power exists at different frequencies, across a given frequency span. Maybe a good way to think about it is if you have an old FM stereo in your living room, right? The old ones that had the slide rule dial on it and had a signal strength meter sitting next to the slide rule dial. So you knew when you tuned down to a station, the signal meter went strong, right? If you plotted out that signal meter strength versus your position across the dial, that's like plotting out the trace on a spectrum analyzer.
And essentially that's how basic spectrum analyzers work. They have a tunable filter, and they sweep the selected frequency range, and then they have a peak detector that then follows on to basically measuring the absolute value of whatever signal's coming in.
Absolutely, and that's actually therein part of the problem. Okay, so if you take that same analogy of sweeping your radio receiver across a span, or sweeping a filter from a start frequency to a stop frequency, what happens when you've got a transient or low duty cycle signal and it doesn't happen to be transmitting when you sweep past it? You don't see it, right? Yeah. The spectrum, I like to say that a conventional swept spectrum analyzer can only see what it sees through the eyes of the resolution bandwidth filter as it's sweeping across. So if something is occurring on either side of it, when you're sweeping, you don't see it. Okay, so and that's part of the problem. In fact, we could bring up a display here that looks a bit more like a conventional spectrum analyzer, because this is probably what more people are used to looking at, is that. Okay. Right. So this isn't really sweeping either, but it's kind of more emulating what's going on. Now I'm looking at the exact same frequency space, same span, same center frequency that I was looking at before. But you look at this and say, well, hey, looks like most of the time I'm just seeing noise floor, except for this little, peak right here. Most of the time I'm just seeing noise floor. And then every few seconds I'm seeing another burst popping up here. And this is part of the problem, is this is kind of what you see with your conventional swept spectrum analyzer. It's blind most of the time. So when you have these low duty cycle signals that are out there, because gone are the days where everything is broadcast, like your AM and FM broadcast or TV broadcasts are typically analog things. They're on all the time. They're easy to go put on a spectrum analyzer and look at. But when you start talking about Wi-Fi, Bluetooth, Zigbee, LoRa, all of these other wireless interfaces now, none of them are continuous broadcast. They're all bursts, right? Wi-Fi bursts are typically a couple of hundred microseconds long, and they might repeat every 100 milliseconds. Very low duty cycle bursts. So you might have to go in and play some games, like maybe I go in here and turn a max hold trace on and eventually build up the envelope of everything that's going on. But again, this still gives you a little bit of a distorted picture of what's going on in the frequency space, because you really can't see what's making up all of this. So how does a real-time spectrum analyzer differ? Well, you could say, well, it just sweeps really fast, but that's really not how it works, okay? So a real-time spectrum analyzer works by essentially, instead of sweeping a narrow filter across a frequency span, it's essentially a wideband receiver. So we're taking a given frequency chunk of spectrum, down converting it into some kind of an IF, and digitizing that whole chunk. It's like being able to look at the entire FM broadcast band at once, okay? Digitize that whole thing and then mathematically compute the spectral content using either a fast Fourier transform or chirp-C transform or something like that, some kind of a discrete Fourier transform typically. So once you've got that concept of a wideband acquisition system, and this is the same concept of an SDR or software-defined radio. This is kind of how they all work, right? So you basically have a wide enough capture bandwidth or analysis bandwidth to encompass the frequency range you want to look at, and then you're doing everything else in DSP. So once you're doing that, you can say, well, I can just compute spectrums, and now if I compute spectrums fast enough, so there's effectively no gap from one spectrum computation to the next, now we can start calling it real time. The problem with that is that once you start doing that, you might be doing tens of thousands of spectrum measurements a second, or maybe hundreds of thousands of spectrum measurements a second. Well, you can't update the display tens or hundreds of thousands of times a second, right? So what do we do, right? Because even if you could update the display, your eye couldn't perceive it.
Your eye went right.
Right. So what we do then is basically take those tens of thousands of spectrum measurements a second and lay them all on top of each other. Okay, and essentially a pixel bitmap. And then about 30 times a second, look through that stack of spectrum traces, okay, and assign a color to the overlap or the density. So if you think about, you can almost think about if you drew all these spectrum traces on a piece of paper, okay, the places where you wear through the pieces of paper, right, that's this area here that looks like it's in red. Okay, where you have most of the overlap. That's the highest density of these traces laying on top of each other. And then you work your way down from the red to the yellow to the green to the light blue to the dark blue. You're looking at less frequently occurring things.
Yep.
Okay. So this gives you now kind of a view of what's going on in the RF domain in a very live sense. I like to say it lets you see what your receiver sees. Okay, we're looking at a portion of the 2.4 gig ISM band here. Now, I'm only looking at a 40 megahertz span. You say, well, why am I only looking at 40 megahertz here? Because this happens to be the widest instantaneous or real-time bandwidth for this very inexpensive analyzer that I'm using here. Okay, there are real-time signal analyzers that go up well over several hundred megahertz of bandwidth, and I've got one that I can bring up later on that's got about 165 megahertz of bandwidth, but this one's got 40 megahertz of bandwidth. It's a very inexpensive.
And what analyzer is this?
So this is a Tektronix RSA 306B.
Okay,
so it's
same one I have basically.
Yeah, so it's a 9 kilohertz to 6.2 gigahertz frequency range with a 40 megahertz instantaneous bandwidth. Now, of course, I can take this and I could do a much wider span, like just a conventional spectrum analyzer, right? There's a 1 gigahertz span that I'm making a measurement over. It works just like a swept analyzer when I do that. But once you get down to that magical real-time spectrum analyzer bandwidth or span, then things can go live. Okay. So if I may go back, and in fact, I could even take, and if I maximize, let me maximize this, the real-time display. I can actually make this span wider too, and what you can kind of see it stitching its way across in 40 megahertz chunks. Okay, so I can do a wideband sweep to look for all this transient activity and things like that. But again, once I get down to that magical 40 megahertz, in the case of this instrument, it goes live, because now it doesn't have to stitch and tune; it can stare and compute tens of thousands of spectrum measurements a second and throw it on top of each other. So that's what we're looking at in terms of hardware. So what are we looking at signal-wise? So we're in the 2.4 gig ISM band. This is, about an 80 megahertz wide frequency band that stands for industrial, scientific, and medical. Everything from wireless LAN, Bluetooth, microwave ovens, Zigbee, and dozens and dozens of other wireless interfaces live in this frequency space. So I tend to refer to it as the commercial equivalent of electronic warfare. Right, because everything is competing for space here. So what we're looking at actually is, this is all down in my home office lab. So I've got a bunch of things running down there. There's a test board that's generating a signal at this frequency here, about 2.445 gigahertz or so is about where that guy is. I've also picking up some wireless LAN activity. There's an active wireless LAN channel right here. And you see this little wiggling thing going back and forth, zigzagging back and forth here. That little wiggling, zigzagging back and forth thing is actually the little hockey puck transceiver that is looking for my my wireless headset that I'm not using. So since the wireless headset's not paired up with it, it's just hunting back and forth looking for it. So it's just hopping across these multiple channels back and forth, trying to find, where's the headset? Where's the headset? I want to pair up with it. Okay, but it's it's digging up about, or occupying about 20 megahertz worth of my 2.4 gig ISM band, just sweeping this signal back and forth, looking to see what's going on. Okay, so in fact, we could do some cool stuff. We can actually take and strip chart this in what we call a spectrogram or waterfall display. In fact, let me stretch this out in time.
Which somebody's already asked about. Yep, in the chat channel.
And those are a favorite toy of Ham's now.
Oh yeah.
Even a lot of transceivers have this capability built in.
Yep.
Except that it's not necessary.
Our waterfall goes up. All the ham radio transceivers and the software SDR radios, all the waterfalls go down, hence the name waterfall. Our waterfalls go up. That's just the way it is. So now you can actually see that wiggling signal back and forth here, all right? And I can even see the little stripes in here. In fact, let's stop this here for the moment to kind of show you what's going on here. And I'm going to go into the bitmap and turn it off for a second. And if I right click and throw a marker in here, I literally can just go see what the spectrums are doing at any point in time.
Oh, that's cool.
That's cool.
So I see these narrow little stripes like right here. That's that short little wireless burst. Boom, right there. See, I can find it one spot there. Boom. Okay, then that rectangular spectrum. Let me go turn everything back on here again, and maybe I'll go turn the bitmap back on again. So this rectangular looking spectrum is typically a wireless LAN. It could be 802.11g or 802.11n, for example. And the rectangular spectrum with a little bit of a null in the middle there is kind of a signature of an OFDM transmission, orthogonal frequency division multiplexed RF signal. What that fancy name means is that this is composed of many what we call subcarriers, each one of which are being modulated, and they're all arranged such that they don't interfere with each other. They're kind of, that's hence the name orthogonal. They're orthogonal to each other, but the idea is that you send, it's kind of like the RF equivalent of a parallel port versus a serial port, right? If you take all of your data and you put it on a single carrier and send it out, and you want a high speed, you need a high symbol rate going along on that high speed single carrier. That's just like a serial port. You're sending all your data through one lane. Versus, say, an old parallel port, where to get the same volume of data across, in a parallel port, you can slow the data rate down because you're sending 8 or 12 or 16 bits at a time, right? Through one, so your data rate can be much lower. So OFDM works the same way. So a single carrier RF modulation would need a high symbol rate to get all your data through, but I can get the same data through by sending it on multiple subcarriers at a slower rate. And the benefit there is that it's more immune to transient interference because of the symbol times are longer, and you only interfere with a portion of the symbol time, you're less likely to kind of lose the data.
I assume that legal power transmission levels play into this too, because ISM band communications unlicensed, and you need to maintain a low power level. So to get more information to go further, you need those multiple channels and spread spectrum as well, right?
Yeah, so we're looking at one channel here where, the Wi-Fi is at 11 channels or 11 or 13 channels or whatever in the US. So each of those channels is 20 megahertz wide, but within that 20 megahertz, all right, we have this OFDM signal that's got 50 subcarriers in it. Okay, so but then every once in a while, I call this a Bart's head spectrum because it kind of like Bart Simpson's head. Right? It's kind of squared off, right?
Like
so that's
that.
the Bart Simpson spectrum, or the Bart spectrum, but then every once in a while you'll see kind of a more rounded spectrum that pops up in here. In fact, let me tune over here a little bit. Let me just kind of pan over and let's look at a different spot in the spectrum. In fact, here I can actually see a more rounded spectrum. Okay, and that's kind of like a Gaussian shaped spectrum. That actually uses a different type of modulation. It's called a CCK modulation, which is kind of a variation on just a single carrier BPSK type thing. But so you'll start, the more you play with the stuff and you look at things in real time, you start to recognize what these various signals are. Okay, I can tell this is this is 802.11b. And most routers, even if you've got an 802.11n or 802.11ac router or something like that, the beacons it sends out to say, I'm here, do you want to pair with me, are typically sent out with 802.11b. So the idle, if you will, is a bunch of these 802.11b bursts. And then once you're sending data, you're typically going to be sending data through some kind of an OFDM signal, okay? And then the modulation type of the subcarriers is going to depend on the signal quality that's assessed between the access point and whatever wireless interface you have. So it might be as simple as a BPSK or QPSK modulation, on those subcarriers, or all the way up to 256 QAM or some other more complex modulation on each subcarrier, depending on the signal quality level that's been assessed when it establishes that connection. So
there's a lot of layers and configuration that has to go on.
Yeah, so people say, well, why isn't my Wi-Fi working? Well, you're living in I'm in a household here, I'm on a 1/4 acre lot, and it's just me and my wife. Okay, so we don't have a ton of stuff going on here, but this is all the stuff that is going on in the 2.4 GHz ISM band in my house. Can you imagine when you get into, commercial buildings, or you're living with other people and everybody's playing gaming on their stuff? It's a wonder that this stuff works at all. Okay,
yeah, right.
So,
yeah, that's why I say that it's like space junk. Yeah,
we keep adding light bulbs to it.
Yeah.
So you might have 20 Wi-Fi or 30 Wi-Fi devices in your house all on one network too.
Yeah, I'm
And,
going to actually pause. You notice I'm looking down at my phone here. What I'm going to do is I'm going to send a text note down to my wife and ask her to go turn the microwave on. So we'll see the
Oh.
microwave up kind of showing here. Um, so it's rather than me run downstairs.
Or yell loudly, yes.
Yeah, that's true.
So, just
So-
talking about ISM bands and band allocations, I'm pretty sure that's a band allocation chart on your wall behind there.
Oh yeah, yep.
But
Oh, there's the
ISM,
microwave right there.
I see ISM is not just the 2.4 and 5.08. There's
Right.
there's other sections in the band, but based on what you know, how and why did the FCC allocate those to unlicensed, science and technology and experimenters like us?
Yeah, well, actually, there's a microwave here. I just want to kind of point that out. You see this little thing that looks like it's a wind-driven water fountain that's wiggling back and forth? That's what the microwave ovens look like. Okay, and then you can see they're spreading out over the entire band. So, why does my Wi-Fi drop out when I'm heating up my coffee? That's why, because you got a 1500 watt transmitter and a not very well shielded box. Okay, so
That's a worry.
yeah, oh yeah, and I'm the kitchen is sitting below me, so I've got a whole floor between me and well, actually I should say, well, the analyzer we're looking at is sitting in my home office, which is 2 rooms away from my kitchen. Okay, but I can see that's my microwave oven right there. Okay, it's as strong as the Wi-Fi signal that is 2 rooms away from the microwave oven. Okay. So anyway, and you can actually see it wiggling around here over time, but yeah, they're pretty unstable, and this is why they can wipe out your Wi-Fi or your Bluetooth. Anyway, you're asking about the ISM bands. So the ISM bands were really not developed for amateurs, but they were developed to be kind of wireless interface spaces for just what the acronym says: industrial, scientific, and medical, and of course other license-free services like Wi-Fi, Bluetooth. Typically short range type of things, low power, short range type of things, and there's a number of those license free bands. There's a Wi-Fi. There's a license free band at right around 13.56 megahertz, and that's where a lot of your like RFID and wireless pay like Apple Pay and things like that. All that stuff works at 13.56 megahertz, near field communication type stuff. And it's typically magnetically coupled, not really an RF thing, because I don't have an antenna on here that's really efficient at 13 megahertz, because it would be a huge antenna, right?
Yeah.
So
totally.
they're typically near field magnetically coupled things. Probably the next big wireless band, there's a number in the 400 megahertz band, and this is where like remote keyless entry systems for your car and things like that typically will operate, in the 300 to 415 megahertz type area. This is where you see a lot of those things. The next kind of larger one is in the 900 megahertz band. There's a 28 megahertz wide ISM band, and this is like a lot of industrial controls that use like a Zigbee protocol and things like that. And even some of I think LoRa will operate there as well, the LoRa. I don't know if you guys have ever talked about any of that technology or not, but that typically lives in that 28 megahertz wide 900 megahertz band. The 2.4 gig ISM band is kind of the king, where everything lives, Bluetooth, Wi-Fi, all this stuff, microwave ovens, everything all kind of lives there. And then you got the 5 gigahertz, ISM band where a lot of Wi-Fi is as well. And there's probably a couple of other ISM bands that I'm not even thinking of, but they were kind of set aside to be bands that are intended to be low power, license free, and you got to accept the interference that you get, right? Because everybody's in there, everybody's kind of competing for performance and operation in this space, and it just is what it is. So, but
how long do you think we can continue piling stuff into that band before it becomes like space junk, and you just can't you can't fly without spending lots and lots of money yourself?
Yeah, I mean that's the problem. I think there are areas where you already have that problem, right? It all depends on how active things are. Now, a lot of the systems, like my little thing that's hunting around there looking for my headset, it's kind of cognitive, if you will. What it'll do is once it pairs up, it takes a look and says, "Hey, am I clear here? If not, I'm going to change to a different frequency." Like even like my cordless phone usually uses a DECT frequency, and that's in the 5 gigahertz range. It actually tries to pair on a clear channel. Okay, so
right.
they're kind of cognitive to try to understand what's clear and what isn't, and try to fit in a hole. But then you have some applications like Bluetooth, for example, Where Bluetooth basically sets up, like Bluetooth 2.0, for example, has got 79 different frequencies that it hops over, and it has its own little hopping pattern. Okay, and so that's why multiple Bluetooth devices can exist, because they all have different hopping patterns, and they're not hopping on top of each other. But they don't spend more than a few hundred microseconds at any given frequency, so they don't cause enough interference oftentimes, and anything that's dropped is often enough that you can kind of account or just ignore, because other channels will kind of make up for it as it hops around. So there's all these different techniques that are used.
Right, I had counterintuitive example where I got those Hue lights. Ben mentioned light bulbs, and when I moved the Hue transmitter to the other side of the house, away from my wireless transmitter, things got worse because it couldn't see it. It's tried to use the same frequencies. So I move them close together, and it becomes cognizant of each other, and they start cooperating. But when I moved them far apart, the interference got worse. And it was counterintuitive till I figured out what was going on.
Oh, yeah. And this is where being able to understand and see literally what your receiver sees, understand the adjacent and co-channel interference and that type of stuff in a very live sense, can give you a lot of insight to where some of these problems lie. So, so that's kind of why most RF signal analyzers these days have the ability, if not to do real time, they have the ability to capture, a record of seamless data over time, so they can look at, see how things are changing over time.
It's at some point receivers act like the spectrum analyzer in that there's a bandwidth of that it can accept, and it can become overloaded by frequencies that it's not even interested in if it's too wide.
Yep, exactly.
We're coming up on that point. It feels like it's kind of, as you called it, this commercial warfare here at some point will all be on a different frequency.
Right. Well, that's kind of why the 5 gig ISM band is starting to become more popular for 802.11 AC, for example, not only because of the increased bandwidth, but just the fact that it's not being used as much. You might have better luck, getting your devices to work connected at a higher speed using that. So
yeah. As an engineer, it sounds like it all leads to the same place, which is interference to me. How do we stay ahead of it?
It's also why every house I've owned, I've gone to the painstaking trouble of running Ethernet cables to pretty much every room.
Yeah.
Yes. Same here.
Oh yeah.
I have a 48 port switch that's full here. Yeah.
Yeah, I'm up on the second floor here. I run a hard line up to here. Comes Cat 5 up to here. Because the Wi-Fi here is not very strong, and I get a stronger Wi-Fi signal up here from my neighbor's house than I get from my own house. So I'm wired up to here, but like I said, it's just one of those things that it's the nature of the beast these days, and you really kind of need the tools to go look at that stuff. So, but it's some pretty cool stuff.
Oh, that's a cool.
This is kind of turning it in a 3D view, so you can kind of see how things are moving. So.
Yeah.
It's kind of a 3D waterfall type.
The spectrogram is also used frequently in audio analysis.
Yeah.
So it's the same principles.
Yep.
Just different frequency ranges.
Yeah, you're just collecting, it's a strip chart recorder of spectrum traces, and you're kind of looking down at the amplitude of those traces, like a big ham sandwich, right? You're looking at the edge of the ham sandwich there. And
sandwich.
Right. And there you go. Yeah. And then when the marker can pull a particular slice of ham to look at it.
And I have used the same analyzer down in the upper audio frequencies. I wanted to look at something around 15 to 20 kilohertz. Yep. And rather than dig out my old audio spectrum analyzer, I grabbed my Tektronix. Yeah. And it worked well.
Yeah, so I'm going to switch gears for a second here. Let me see if I change what I'm sharing here. I guess I stopped sharing. Hold on a minute. Let me go share something else.
Still looks cool though.
All right, so let's see. I think let me pull up this guy.
Okay, we see that.
Sweet.
All right, so this is now a benchtop real-time spectrum analyzer. This one has a 165 megahertz instantaneous bandwidth. They're sitting, obviously you can see there's an antenna sitting on it. I'm looking at about the same frequency range, but now I can see 800 megahertz worth of spectrum. Let's go in. Let me go make this a bit more
Oh,
sensitive.
and that hunt
preamp
pattern
on.
looks a lot more recognizable that you were talking about from your wireless earbuds or wireless headsets there.
Yep. Yeah. So now I can kind of see that going on. This isn't located as close to that wireless puck, so I can see the power levels changing just over that frequency range here. But I can see some other things going on. And the other benefit of this, of looking at things with real time, is that you can see, signals underneath other signals, right? Because they're existing at the same
Right.
frequency, but at different points in time. Okay, and that's just something you can't do just with a conventional spectrum analyzer.
Right, and that's defined or visible because of the binning and the brighter points, or the red colors versus yellow,
Yeah.
green.
The color grading and things like that. So being able to see like there's a little tiny signal sitting here. There's one kind of sitting right here, sitting underneath the skirt of this wireless LAN signal that's going on. So
Yeah, it's a lot clearer than it was. When I was in college, first studying electrical engineering, the college was running on the smell of an oily rag.
yeah,
And so they had some good, well-maintained equipment, but it was old analog digital phosphor scopes
yeah,
and analog phosphor scopes and analog phosphor spectrum analyzers, and it
Okay.
was much harder to pick these things out back then.
yeah.
It's come a long way.
Oh yeah, it's pretty incredible what you can do now. And this
So-
is kind of
so-
what I would call a mid-range benchtop analyzer. There's high-end benchtop analyzers that go several hundred megahertz of instantaneous bandwidth and things like that now too. So
Question.
So which analyzer is this?
this
What's
is an
the
RSA.
full name?
So the RSA, this is the RSA 5126B. So this happens to be a 26.5 gigahertz spectrum analyzer, but it's in the RSA 5000 family of Tektronix analyzers.
Okay.
So
So, what kind of budget would you need to get started with a low end or a mid range?
So the one we were started off with, the USB based analyzer, that RSA 306, he's about a $4,000 analyzer.
Right.
Okay, and it's basically it's about the size of a small paperback book. It's connected by a USB 3 cable to your PC, and you run the software in your PC.
Not
So
bad.
a little bit smaller than what Bill's showing there. That's actually a VNA. But the
Oh, is that my VNA?
that's your VNA.
Whoops.
So
Keep talking,
the
I'll pull out
analyzer
the
we're looking at
spectrum.
right now, the RSA 5000, is a benchtop instrument. Starts for the lowest bandwidth, lowest frequency version starts at about $30,000. So it's not something your typical hobbyist is going to have.
Yeah. So you need some commercial backing, or a business behind it with some good tools budget.
Yeah.
But certainly not outside of the reach of a standard electronics lab.
No, exactly right. Now, I know that we chatted maybe a little bit earlier about looking at things like constellation diagrams, looking at modulation, and if we wanted to do that, we could start off by taking a little bit of a smaller look at a single carrier to understand what the modulation looks like, and then maybe go into something like an OFDM. Does that make sense?
Yeah.
Yes, yeah, we've already got a question. Chris is asking in the chat channel about phase coherence and phase in general and offset and things, which sounds to me like it gets a great segue for what you're about to show us.
Yeah. So so let's talk about we will do a single carrier simple modulation like a QPSK and look at what it means in the time domain, frequency domain, modulation domain. So what I'll do is I'm going to preset.
There's
There it
the
is. There's
small
your 306.
analyzer. Yeah,
That's
Yeah,
the one we're
took me
looking
a while.
at first. That RSA 306 right there.
Right.
Yep.
it's so small it took me a while to find. Yeah.
All right, I'm going to preset my analyzer here and give me a second to set up something on my signal generator here. Let's see, let me go drop this waveform in here and go play this. Actually, I need to drop it on a different channel. Let me go, because I got a couple of channels on my signal generator. I know you can't see what I'm doing here, so
Yeah, it's a gray box.
yeah, pay no attention to the man behind the curtain here. So.
Yeah.
So, all right, so what I should be able to see, if I change my center frequency here to a gigahertz, let's see, do I have it going the right place? Oh, it is channel 1. But I've got that playing there too. 1 gig center frequency. Oh, there we go. Now we're playing. But we're not seeing it. I'm trying to remember how I had things hooked up downstairs. So let's see. Oh, here's what we got to do. We got to change my clock frequency here. Sorry. Again, pay no attention to the man behind the curtains.
It's all electrons.
Here we go.
There we go.
So this is a single carrier modulated with what's called a QPSK, which is a quadrature phase shift keyed signal. And it's a very fancy way of saying that we're just modulating it with, we're basically taking a carrier and changing its phase to one of 4 phase states. Okay.
Yep.
In fact, if we take a look at this a bit more carefully, maybe let me go bring up a couple of displays here and see if we get lucky and be able to view this kind of in an interesting way.
Which brings up one of my pet peeves, that people use the words board and rate together like it's a thing. But anyway, we might leave that alone for another day.
So what we're looking at here, I'll just stop this for the moment. Oops, let me go bring that back up here, and let's just stop this here for a moment. A little bit tough to see, but what they're looking at is phase variation in the vertical axis versus time. And I can actually see I've got one phase step here, one phase step here, another phase step here, and then the last one is essentially plus or minus 180, which are effectively the same. So it's bouncing back and forth between the top and the bottom. So it's really 4 different phase steps that we're sending that carrier through. And because we have 4 phase states, each of those states can represent a 2-bit nibble.
Yep.
Right. So I got 0, 0, 0, 1, 1, 1, 1, 0. Okay. So this is what it looks like just from a raw phase versus time standpoint. In fact, I could probably knock my span down here a little bit. Maybe I'll clean things up a little bit here. Let's kind of do that. But now if we actually want to go look at what this looks like in terms of modulation characteristics, we can actually go ahead and do that as well. So let's start off with looking at what we call a constellation diagram. And I just need to go tell it what it is that we're looking at here. QPSK at 1 megasymbol per second. And let's see. And let's see.
I love it.
Yeah, so that's typically what happens if you don't get the filters and such set right here. And you know, the part of the problem is that I have this. I was hoping this would work, and it looks like it probably isn't. And the reason for that is I've got the antenna and the signal generator going into the same port.
Oh.
And I'm getting probably too much interference off of the antenna to actually properly demodulate.
Right, but I do note that in the constellation, every now and then I'm seeing 4.
You're seeing the 4
yes.
points. Yep.
Same here. Yeah.
Right, so that's what we're looking for here, because it
All right,
represents the quadrature of phase, right?
There it goes.
So what I'm going to do instead, I'm going to turn the signal generator off, and we'll actually go try to demod some of the Wi-Fi off the air. Okay, that's also a little bit dodgy to do sometimes, but let's go play with that. So I'm going to preset this analyzer here. Let's start with it here. If it doesn't work, we'll go back to the other one, which is a little bit closer to the signals here. But let's go. We'll just go play with this and see what we can get. So let me go bring my reference level down, turn my preamp on. Okay, let's look at things with the real-time display so we understand what's going on. Okay. All right, so I've got a pretty strong signal right here that I'm likely to be able to trigger on. So what I'll do is I'm going to just make life easy for me and center myself right up on that. So I'll just set that to the center frequency. I'll knock my span down here. There's a 20 meg. Let's go to a 40 megahertz span, which will probably be good enough. And of course, we got to wait for the alignment to happen, because that always happens when you do a demonstration. The alignment will kick off. And it's one of those things that takes about a minute to run, but it takes 5 minutes if you watch it. So don't watch it.
Okay. Well, it's pretty. I'll give it that.
There you go. So what we'll do, we'll see this particular channel is a pretty active channel out of my router. That is, you can see a combination of a couple of things. I can see my 802.11b beacon in here, as well as an 802.11g. In this case, I happen to know it's a G OFDM signal going on. So they'll bounce back and forth. So what we'll do is we'll try to trigger on at least this burst, and then sometimes we'll demodulate it, sometimes we won't, because sometimes it'll be what we picked to demodulate, and sometimes it'll be the other format. But I can actually see some of that activity in here now. So let's go. What we can do is set up a way of going to capture the particular data or spectrum of interest. I'm going to bring up a couple of displays to help us go view that. And I'm going to do a fancy little trigger here called a frequency mask trigger, which is going to allow me to trigger on the shape of the spectrum. Okay, so
that's cool.
So if I bring up my real-time spectrum trace here, I can see I want to trigger on something going on here in the middle. So if I start with a new mask and I just start moving some points around here and just pull these guys down here and trigger only when I got energy coming up into this area, right? I'll get these up out of here. So I'm only going to trigger when that event occurs. I'll say, okay, I'm done, trigger, and now start capturing some data over time here. So now I can actually see some bursts going on in here, right? So this display up here is showing me RF amplitude versus time. All right, so we're going from nothing being turned on to the pulse coming up. And if we stop this here for the moment, you can actually see some structure in here, right? You see a little bit of something that looks kind of unique at this front end of this, kind of regular. And this is actually the preamble in the burst before the actual data payload is being sent. Okay. And what's also kind of cool is we can look at this, let me kind of stretch this out over time here. We can actually see what the spectrum looks like over time. In fact, if I throw a marker in here, okay, and if I pull that, position that marker kind of towards the front, you'll notice the marker is sitting kind of right here. As I drag that marker down in time, look at what the spectrum is doing during the preamble. Only some of those subcarriers are on. You can start to see some individual subcarriers there. You can see some structure and some pattern to this preamble. Okay, and then you get the random data packet that's following that. Okay, but now let's go demodulate this so I can see what we've got going on here. So let's go here and do the wireless LAN analysis. Let's add a constellation diagram, maybe a symbol table. Now I might get too many displays. I might turn some of these off. Let me go let's go tell it what it is we're looking for. 802.11g 20 megahertz. So that should be good. I should be able to just go look at that. And yeah, so I can actually see some modulation in here. Let's just go run this. And you'll see some signals demodulate. We're trying to demodulate stuff off the air, so it's not going to be perfectly clean. So what a constellation diagram shows you, it shows you essentially a combination of magnitude and phase of the carriers. Okay, so think of the modulation diagram as like we call it a polar diagram. The center of this diagram represents 0 magnitude. The further you are away from the center, the larger the magnitude of the carrier. Okay, and if you drew a line from the center to a particular point, right, the length of that line is the magnitude. The angle of that line off of, say, the x-axis is the phase. So it's a way of looking at magnitude and phase. So in this case, we're looking at 16 different symbol locations. We'll ignore these two guys on the corner, which are pilot tones. You've got a grid of 4x4, so we have 16 possible symbol locations, right? So that's a 4-bit nibble, right? 0000 to 1111, okay? 16 possible locations. And each of those nibbles or each of those symbols, okay, or nibbles, are represented by a particular combination of magnitude and phase of the carrier. Yep. Now, the reason I've got a couple of dots in there is because there's a couple of symbols that are landing there, but also I'm looking at, remember I mentioned this is kind of an RF parallel port, right? So I have multiple subcarriers transmitting symbols, and this is showing me the combination of all of those. Okay. And in fact, if we take a look, for example, at my symbol table here, if I maximize that, what this is showing me is, here's my subcarrier numbers across the top. So I've got -26 to +26, so there's 52 subcarriers. Okay, so 50. Wow. So instead of having a single carrier, we have 52 carriers all sitting next to each other. And it's only, in this particular case, I'm only sending 2 symbols. So in subcarrier 26, it has a symbol D and a symbol F. Subcarrier 25 is D, is 6 and D, etc. And if we look at, if I click on this, you see where I just clicked on that particular one. It just positioned the marker where that guy is.
Yeah.
Right.
Wow.
Now I've got that one right there.
That is cool.
Okay. but now we could also look at some interesting things. I'm going to turn off a couple displays now because we're going to get too much. Okay, let's look at a couple of other interesting things here in terms of breaking this down. We'll look at EVM and yeah, maybe just that one for now. Okay. So let's go run a couple of times here, and I'm going to replay myself back because I'm storing all these acquisitions in memory, so I have a way of essentially going back and also grab one that actually demodulated cleanly, relatively cleanly, and auto scale that result here. Okay, so what we're looking at now is, remember, each of these dots represents a particular symbol that was transmitted by a particular subcarrier. Okay, now we note from the symbol table that this short little burst is only transmitting 2 symbols. Okay, so symbol 1, symbol 2, and that's, well, I should say 2 symbol times, but I've got a number of symbols being transmitted, you know, at the same time in parallel.
What are the yellow blocks?
So the yellow blocks here are what are called pilot tones. So they are also subcarriers, but they're not carrying data. What they're carrying is a very simple modulation, in this case just a binary phase shift keyed signal that the receivers use to align phase and amplitude.
Yeah, that's
So
your
they're-
reference to know what the
Right.
different symbols actually are.
Exactly
Yeah.
right. So it's a phase and amplitude reference to help demodulate the rest of the subcarriers. So that's why they're coded in yellow.
So
But the
yeah, it
rest of
was
them
asked
actually-
in the chat if they're also called the guards.
Now there's a guard interval that's actually part of the packet structure, but it's not really a guard. Okay.
Okay.
So, but so it's really part of a packet structure to keep collisions and stuff from happening. But the pilots are there as a amplitude and phase reference for the demodulation algorithms. So because we're transmitting 26 subcarriers, the accuracy, because ideally we'd want all these constellation points to land right on top of one of those crossing points, right? But they all deviate from that at some point. If we actually drew a vector, a line from the ideal symbol location to the actual symbol location, right? The magnitude or the length of that line is called the error vector magnitude, okay? And that's what we're plotting up here. So this is plotting error vector magnitude 2 ways.
Noise, in other words.
Yeah, it's noise. It's deviation from the ideal symbol location, okay? So that error vector magnitude can be measured 2 ways with an OFDM signal. We can measure it by subcarrier, right? So on subcarrier 26, there's where the EVMs were for the 2 symbols. So each of these subcarriers has 2 symbols on it, right? So I got 2 symbols in each column, and I've got 52 columns here for all the subcarriers. So this would allow me to look at, if I had problems with bandwidth of the amplifier, for example, I might see more error at the frequency edges than I do in the middle. Okay, if I had a frequency flatness problem, right?
Right.
So that allows me to look at error essentially across the channel bandwidth. Okay, where this plot up above is showing me error by symbol. Because since I've got all those symbols that I've got across this whole column, all 26 or 52 symbols, well actually 52 minus the pilots, right? All piled up here for symbol 0, for symbol 1. Okay. Now if we go and run this, we may eventually, we get a couple in here. This didn't demodulate exactly right. We're trying to do things off the air. Sometimes it's tough. Here, this particular packet, instead of sending 16 QAM, sent QPSK, 4 symbols, okay, or 4 symbol locations. It sent 3 symbols using QPSK. All right, so now I've got 3 symbol times. So now I have 3 symbols up here. And I also see a little bit of variation in frequency, which means I probably have some interference going on in that channel. Good. Like commercial equivalent electronic warfare. And you're typically, if you're measuring the modulation quality of a wireless LAN signal, you're not going to be doing it in this very uncontrolled way where I've got an antenna picking up everything else. So it's kind of unfair to try to make this kind of pick up things clean. But you can kind of see it bouncing back and forth between different modulation types here, right? In fact, I can go through and go look at some previous acquisitions here. Okay, so there's some 16 QAM, some QPSK. I thought I saw one higher order, like a 64 QAM, but maybe I didn't. There's another 16. Yeah, so I'm just picking up previous acquisitions here. So here's one that actually went BPSK and actually went longer. I didn't capture the whole thing. And you can see it actually, in this case, captured how many symbols here? So 8 symbols, and it probably was transmitting more. So this particular case, it figured out that, hey, I've got a little more interference here. I got to step down to a simpler modulation protocol. I'll transmit longer to get the information across. So instead of running at 54 meg, it was running at 5 meg or 10 meg, on that particular Wi-Fi burst. Okay, but this is the kind of analysis you can do with essentially this is a vector signal analyzer. This is kind of what you do with this stuff.
That is way cool. So what kind of antenna are you using on this? Because if the instrument has 160 megahertz bandwidth, but it spans basically
DC to 26 gig, yeah.
or 26 gig. Yeah. So you obviously need a range of different attachments that target the application. So what are you using right now? Because is it just a cheap Wi-Fi antenna?
It's not even that. It's a cheap rubber duck antenna like this one that come off a handheld ham radio transceiver. So it's not tuned to the 2.4 gig ISM band. It was geared for VHF and UHF ham radio use, like this guy right here. Okay, so totally the wrong antenna for doing this, but. At the end of the day,
still picking up some meaningful data, which is cool.
At 2.4 gig, the wavelength is about that long in space, right?
Yeah.
So a paperclip would do as an antenna. But I'm not going to stick a paperclip in the very expensive connector in the front of my spectrum.
Calibrated paperclip, yeah.
But a paperclip and a wet noodle would work at these frequencies, right? The higher you go in frequencies, everything starts becoming an antenna, right? So, but anyway, some pretty cool stuff.
That's way cool.
Like I said,
I'm exhausted.
Sorry?
I said I'm exhausted just from following and watching all of this. This is very cool.
I feel like we barely scratched the surface and we're already coming up on an hour. But I did want to make sure we had a chance to discuss a little more about, because I mentioned before we started streaming, there's a number of people on our stream who are already professional engineers. Some are hobbyists. And some are students or people aspiring to sort of explore this as a career. And I fell in love with electronics when I was 8 years old, and my big brother was an electronics technician for a TV station. Yeah. And he bought me my first soldering iron, showed me how basic components worked, and I was hooked right from an early age. And I feel like the passionate people in our industry are like that, but we have some of them in our Discord and tuning in. So any advice from someone who's really a seasoned expert and knows how to get your hand on good equipment, knows how to sort of follow industry trends that are going to keep you employed as well. That's a pretty important thing.
Yeah. So well, I always say follow your passion. When I started off, when I was in high school, I worked in a TV repair shop. And so I learned at a very early age the value of tools and equipment to kind of dig in, and the value of just good practical knowledge that unfortunately is not what you typically learn in the university. What I found that for university, you get the basics, the fundamentals, you understand the laws of physics and Ohm's law and how the various devices work and things like that. But the other thing that, to me, the real value of what I learned in college was the methodology of how to approach problems. Okay, kind of the engineering thought process. Not necessarily you come out and I can design a Wi-Fi transceiver. No, you come out with the basic knowledge of how to approach problems. The rest of it is all just practical stuff, and a lot of it is following your passion. Because if you're not passionate about what you're doing, you're just going to go through the motions. You can still get very good at it, right? But it might not excite you. It might not be the thing that you're really going to dig in and try to learn as much about as you can if you don't have the passion for it. So I think you want to follow your passion. And for me, it's always been electronics. As you kind of see from the virtual background behind me, my lab is, that's just built up over 40 years of just collecting equipment and picking up stuff that's broken. And I had a the guy who's left us, who was an application engineer for linear technology, a really fantastic guy named Jim Williams. Anybody who's read any of his application notes, he's just self-trained engineer. But he used to say that when you go to buy a piece of equipment, if it was broken, he'd say, "Oh, I pay more for that," because that becomes an opportunity to learn, about how to fix something and how to dig in and learn something like that. So, well, I won't necessarily pay more for something that's broken.
Well, you do, but in other ways, right? You pay
Right.
less financially, but more time-wise, but you also
Right.
get more from that.
Right,
Because
right.
it forces you to figure it out.
Yeah, and to me, the practical knowledge of building things, experimenting, and failing often is really where you learn, right? If you just go down, you design something, you build it, and you test it, and it works, what have you learned, right? You learned you know how to do that, right? But you really haven't learned that much,
I prefer when my prototypes didn't work right away because, like you said, it forces you to go in and look at every signal and verify what you assume are working correctly.
Yeah.
The exception to that is when I do my final rev of the board that's going to production, I don't want that one to be broken. I want that one to be
Right.
perfect.
Right.
But
No,
up until then,
it's very satisfying to apply knowledge you've gained to something and see it work first time. And there's basic electronics everywhere where over time you build up your kit bag and you get, I feel like I get a little dopamine hit from those, but I've discovered another thing. If I hook up a microcontroller and an LCD and start putting something together and it works first time, it's almost always because I'm not the one who actually did the hard work. I'm usually standing on the shoulders of somebody else who took the time to debug everything, write the software library for the TFT. That's just one example.
Right.
And I feel like, if I realize it's 4 a.m. and I'm still gritting my teeth over something, I must be actually engaged in something that matters. So
Yeah.
it's like that's how you can tell if you're doing what you probably are called to do in life.
Right.
That's when you go without sleep without realizing time's gone by.
Oh yeah. Well, that's why I joke. I half joke say that back when I had a real job, before I joined Tektronix, I was a design engineer. I did design integrated circuits and hybrids and analog and digital circuits, mostly high speed stuff. I did some, I did a lot of test development engineering and things like that, and it was fun. To me, I like getting in the lab, pushing the buttons, and twiddling the knobs. Now, I've been with Tektronix, and I kind of half joke that I don't have a real job anymore because I don't develop anything. Because to me, this job is just fun, right? I get to do the stuff I enjoy doing. I help, a lot of my job is to do mentoring and training and troubleshooting with folks and helping them to understand what their equipment can show them to help them do their job better. And they get a great deal of satisfaction out of that. So again, to me, it's not a job. It's like I haven't had a real job in 15 years. So
that's cool.
Very cool. So one thing I'll throw out for people that want access to this equipment, and if you do work for a small company, but let's say a company that's not going to give you a $100,000 analyzer or $40,000, as we used to rent our equipment from companies like US Rental and stuff. And so for a couple hundred, it's still not something you would do yourself, but you could at least get this equipment for months at a time for a fraction of the cost of, convincing your boss to buy it outright.
Yeah. So if you wanted to indulge me, I wanted to kind of show you where things are going.
Oh yeah,
that'd
go
be
for
cool.
it.
Okay.
Absolutely.
So let me change what I'm sharing here one more time. Let's see. Let me switch my sharing window to this guy, and you should see an oscilloscope screen here now.
Got it.
Okay.
Little gray box. Yep, you got the gray box. Yep.
Yeah, I got the gray box. Let me see if I can get rid of that.
Yep, there it goes. You're good.
So, all right. So I can't see you guys right now because I'm full screen with my scope here now. What we're seeing now, and this is kind of one of the latest, kind of generation of scopes from Tech. This is an MSO6 series scope, and I want to kind of show you two things here. Is we're taking the ability to use what you would typically use with a spectrum or with an oscilloscope to look at time domain waveforms, make measurements on them, all the things you typically use a scope for, but now adding the ability to look at RF in the scope.
Oh,
So this
cool.
concept of being able to have a wideband receiver, this particular scope has got a 2 gigahertz wide wideband RF receiver behind every channel of the scope.
That's incredible.
Okay, so if I go into this channel, for example, I've got probing off of channel 8. It's an 8-channel scope, by the way. So this happens to be a spread spectrum. This happens to be a spread spectrum clock. So a spread spectrum clock is often used in high-speed serial standards, and what it means is that you're taking the clock frequency and ramping it up and ramping it down and ramping it up and ramping it down back and forth, like in a sawtooth, frequency modulating it back and forth.
Yep.
And the only reason they do this is to avoid EMI problems, because the EMI standards haven't caught up with the fact that, you know, the EMI standard says that if I look at this frequency for this amount of time, I can't have more than this power level in it.
Yeah, it's
Okay?
cheating.
If you don't do that, then you pass. So if you cheat by moving the clock back and forth, it never spends enough time at that one frequency to fail. So they use spread spectrum clocks. Oh, it's horrible. Now you're spreading the energy out all over the place. But that's what it is, and you'll find this stuff out there. Okay. So let's look at how we can look at this. So if I go into this channel, okay, and I turn on this feature called Spectrum View, I can essentially get the spectral content of that signal. Now, this signal happens to be living, the center frequency of it happens to be living at 98 megahertz. So I'm going to dial the center frequency to 98 meg, and let me bring the span down here to about 10 megahertz. So now I can actually see this is not a single frequency, it's occupying over a wide frequency range. In fact,
That's cool.
one thing that we can actually go look at here is really cool, is also in Spectrum View, I can look at, kind of like what we did on the spectrum analyzer, I can look at magnitude versus time, frequency deviation versus time, or phase deviation versus time. So if I bring up the frequency deviation versus time, you can actually see it bouncing around. If I go capture some more data over time, you can actually now see that profile. Now what's really cool is I can actually trigger on that. Let's trigger on frequency versus time. So I'm actually triggering on the frequency change of this signal.
Yeah, that's wild.
That is.
To make it even more wild, this particular test board that's generating this, either purposely or inadvertently, this modulation screws up about once every 3 or 4 seconds. All right. So if I go into my trigger system, let's go change the trigger to normal and change the trigger type to a timeout and set the timeout limit here to 100 microseconds or so. And let's start grabbing a little more data over time. Look at that. So here, now what's really cool, let me get one more acquisition in here. So here, this is my frequency versus time, right?
Yeah.
I can actually look at the spectrum at different locations in time. So if I take this little bar right here, this little...
Not exactly spread right there.
Yeah, so if I go over here, there's my normal spectrum that I was looking at before, right? But if I move that spectrum measurement and make that spectrum measurement here, I can see it went to a CW signal, unmodulated signal at about 98.5 megahertz, right? And then about 2 milliseconds later, you see the spread spectrum modulation growing again.
That's cool.
Pretty cool.
That's a Tektronix demo board we're looking at here?
Yep. Yeah, so one of the Tektronix demo board. In fact, if you've got the MDO demo board, it's the spread spectrum clock signal. It's the SS clock signal that's on that board.
So I have to imagine for demonstration purposes, it's intentional.
Yeah, I'm thinking it is too.
It's not documented anywhere. It's not. Nobody's ever documented this. So I don't know if it was intentional or not. There's a lot of crap on that demo board. This might be just crap. But so one other thing I'll show you here.
What kind of devices?
I'm
just curious. What kind of device on that board is generating that clock? Is it a dedicated spread spectrum clock chip from some semiconductor company?
I think there's actually an FPGA that is driving.
It's a Cyclone 2 on mine.
On a synthesizer somewhere.
Okay, gotcha.
Yeah.
But just to kind of show you the fact that all this stuff is implemented in a scope, just going to show you one other, a little bit more complex example here. So here, channel 1 is probing just a trigger signal. Okay. Channel 4 is the RF output. In this case, it's at 2.4 gigahertz. channel 3, I've got a logic probe plugged into it and looking at a 3-wire SPI bus. That SPI bus is being decoded over here. And each of these SPI instructions are instructing a little synthesizer chip to tune to a new frequency.
Right, and so and there you're looking at the different frequency changes on.
Yeah, so now you can see the spectrum as I move this back and forth. I can actually see the spectrum change over time.
Oh, that's cool.
And then this trace down here is the frequency deviation versus time. This trace up here is actually the voltage that's going to the control input of the VCO in the synthesizer.
Yeah.
In fact, you can even I'll take this channel 4 frequency versus time. Let me go grab that and drop it right on top of that. Now I can compare the frequency versus time of the RF to the tune voltage of the VCO that's generating the RF.
That's incredible. What amazing debug capabilities.
Oh,
You
yeah.
had to go that deep.
And you get this RF capability on every channel. Okay, so and then you can go play with the way the display looks and kind of arrange things the way you want them and all that kind of cool stuff, you know.
So what's the cost of this kind of equipment?
So this MSO series of scopes is an MSO 4, 5, and 6. They all have the same capability, just at different frequency ranges. The MSO 4 starts in the the mid to upper, thousands of dollars, like 8,000 or 9,000 if I remember correctly. I don't really know, for the lowest bandwidth units. This happens to be an 8-channel, 10 gigahertz scope. So this is a north of $100,000 scope.
Wow.
So there's a range there.
And engineering managers used to complain about the cost of their EDA software. Come on, let it go.
Right.
Yeah.
Yeah, so this is an employee. This is like your 5th employee here.
Yeah. Well, it's a funny story. I won't name the company, but here's a funny story. You just said that. This is going back about 13 years ago. Had a customer that was looking at buying a high-end arbitrary waveform generator, which was at that time was about $140,000. Okay, and they're doing some work on computing qubit, type of things, qubit research. Okay, quantum computing stuff. So looking at this really high-end arbitrary waveform generator, and they were debating: do I buy the arbitrary waveform generator, or do I hire a grad student to continue my research? And it was kind of this toss-up: where are they going to spend the money? So they actually wound up buying the AWG, the arbitrary waveform generator, and they named it Bob. So I went to visit them about a year later to help out with some stuff, do some training and things like that. And they're like, they showed me what they were doing. So, we got Bob generating waveforms over here, and that Bob is the arbitrary waveform generator that they bought. So,
wow.
Yeah.
What kind of that was a Tektronix waveform generator you're talking about?
Yeah, so that was an AWG at that time. An AWG 7000 series, which has now been superseded by even higher speed generators, but that's what it was at the time. So
wow, excellent.
But,
well, hey, this has been fun, and this was just 2 pieces. Well, actually, we brought in the scope, so 3 pieces of equipment, but this was quite a ride you took us on here, Alan.
it's just I just stopped sharing, by the way, if that's okay.
Great eye candy. Yeah.
So, but yeah, like I said, that's why I said I have fun every day. I get to play with the stuff all the time and push the buttons, twiddle the knobs, show people how to use this stuff. And the thing is, a lot of these things, like some of the aspects of the real-time signal analyzer, being able to see the live real-time display at the same time that you're capturing data and understand what's going on, and looking at spectral content, time domain content, modulation content, all time correlated, or like something like this where you're looking at RF capability, RF signals, command and control signals, logic signals, all at the same time to look at the choreography of all these things. This is the kind of stuff that just didn't exist even just a couple of years ago. So part of my job is to make people aware that you can do this now. So many times I'll hear customers say, "Oh, where was this 10 years ago when I was trying to solve that problem that I had?" But so these kinds of solutions exist now.
Yeah, brilliant.
Yeah, very cool. Very cool. Well, Alan, I want to thank you for stopping by. I'd like to already say, hey, we got to have you back at some point in the future if you're willing.
Sure. Yeah.
So this was a blast. Anything you'd add to this, Ben? This wild ride we just went on?
My head's kind of spinning with
Same
ideas
here.
and thoughts.
Frankly, Captain, I'm exhausted. Yeah.
Yeah, it'd be cool at some point, you know, to dive more into the topic of having the guts to actually get something that you get cheaply because it's broken, but having a crack at repairing. Mm-hmm. And there's a lot of amazing YouTubers out there doing that and showing what they do. Like Mr. Carlson's Lab is another great one.
He's another. Paul does some fantastic stuff. Yeah.
Yeah. But tips on how to and where to look for some of this stuff. I think if I were, you know, up in San Jose, there'd be dumpsters that are full of really amazing, probably fully functioning gear from startups that are going under. You know, they didn't get the third round. So.
But yeah, Hamfest, ham radio flea markets, or even just look like on Craigslist and things like that. Sometimes people have stuff that, you know, they don't know what it is or it's broken. But I look at it and say, if you look at my lab, you know, my virtual lab or my home lab behind me, most of that stuff is 30 or 40 years old. It's all analog test equipment, right? Analog scopes and things like that. And that's all still perfectly usable. You're not going to do what I was showing here with debugging multiple domains and things like that, but I don't do that often on my home bench, right? So my customers do that because they're developing advanced products, you know. But for what I do on my home bench, you know, an analog scope, a decent power supply, a couple of DMMs, and absolutely one or two analog VOMs. You must have, you know, analog voltometers as well to look at trends and things like that. That basic tool set can really take you very far. And there's also, you know, a lot of inexpensive logic analyzer, like from Saley and places like that, for doing some of the bus decodes if you're getting into that stuff. Me, I'm mainly an analog guy, right? I know how to spell VHDL, but that's about it, you know. So, but you know, so you know, the analog stuff is a bit easier. Looks like what is that one? Is that one of the Saley units?
That's Digilant, right?
Digilant, yes. This is my Digilant unit, and I do have a Saley around somewhere. I just don't know where it is. This one's already set up for like an old 6502 was the last thing I used with it.
Okay.
But you know, $100, something like that, maybe 200 through DigiKey. And so what you're saying is absolutely correct. You can find versions of a lot of this to fit your budget, and ask around for people to find out what they use, which is kind of what got our whole Discord channel started, and everything was people coming together to find out other people that have a passion for this stuff. And then a few burnouts like me. Yeah.
So Bill, can you stand up for a sec? I want to get a better look at your T-shirt.
Yes, I'm wearing a Tektronix T-shirt today. This is basically on the MDO. I think I don't know if
it is. Yeah, it's one of the mixed domain oscilloscope, like 6 instruments in one: scope, spectrum analyzer, logic analyzer, bus decoder.
There you go.
DVM. Yeah.
Yeah.
Right,
yeah.
Right.
Cool.
I do have one quick question before we go.
Sure.
On my MDO, we were showing I2C buses and whatnot. Is there a way to trigger on an I2C value? You know, to me, it was treating just like digital highs and lows, and I couldn't say, oh, trigger when I start of a word or something like that.
So if it does require an option. If you actually want to decode the bus and not just look at the highs and lows, you want to decode the bus. There are generally options that are needed for that.
Which I have enabled on mine. I can punch up I2C and it'll show the ASCII.
Panel, there's a bus button. And if you push the bus button, you can configure the bus. And then once you're getting the decodes going and you go into the trigger system, one of the trigger selections is a bus trigger.
I must have missed the bus trigger.
And then once you bring the bus trigger up, then it'll give you the option to want to trigger on a start, a stop, a data value, an address, or whatever it might be.
Yeah, so it's like, just show me when I'm addressing this chip. And then you see, oh, okay, when I'm addressing that chip, I'm getting a NAC. So, you know, there's
yeah, you did, and that was
here,
really the question. How do I see the acknowledge right at that exact address? So I just kicked my scope on. I'm going to try it after the show here.
If I go back, let me go share the scope again here real quick, because this is obviously a different interface than your scope. But for example, if I go into my trigger system here and change the trigger type to bus, it knows that I've got a SPI bus, but if I had other buses, I could pick that, and I could trigger on, a slave select active, or I could trigger on a particular data value, and maybe I want to trigger on a couple of different number of symbols or something like that. In this case, it's looking for it to trigger on a 203141 hex. Okay, so if I zoomed in on my trigger value right here now, if I zoom in on this area here, let's see, I gotta go draw my window so I can zoom in, because I'm not sitting in front of the scope and using the handheld controls here. So let's just zoom in on this area, and let's go zoom in a little bit more.
I can see the blue bursts on the SPI trace there.
Yep. So let me go zoom in a little bit more here. It's a lot more convenient to do this when I'm sitting in front of it, but so
yeah, I just found the bus trigger part you were talking about.
That's what I triggered on right there, right?
Yeah.
So.
Yeah, it's interesting how the analog trace value for the frequency is actually got some noise on it.
Oh yeah, well my probe
exactly
kind of laying
to
right
the
on top
SPI.
of the bus. Yeah, my probe ground lead is laying right on top of the bus traces, I think, probably on the board. But yeah, I can actually see that variation in there. Because if I look at that channel, I'm looking at just 20 millivolts of division, so I'm getting a small amount of variation there.
Get some
I just kind of get this out of the way, kind of open that up a little bit so I can kind of see that a little bit better. So I can get this trace off of here. There we go. So I can make that a little bit bigger.
And here I just punched up as you said, I went to trigger. I missed it before the bus option, and there it can trigger on address 50H. So excellent.
Yeah, you can see I'm getting some crosstalk between my master out slave in digital signal and the control line for the VCO. I mean, these are the kind of things that you can see when you've got a mixed domain scope, where you can actually look at all of these things going on all at the same time.
What's MSO mean? MDO means mixed domain. You said your scope was an MSO.
Yes. This series is called MSO, stands for Mixed Signal Oscilloscope.
Oh, okay.
But to me, I think it really is multiple domains as well. But I mean, that's just what they named it. So there's an MSO 4 series, an MSO 5 series, and an MSO 6 series, and they typically vary by the amount of channels are available, the amount of bandwidth that's available, and in some cases the OS. Like on the 5 and 6 series can be running either Windows in the background or an embedded Linux operating system, whereas like your MDO 3000 and the MSO 4 they're just an embedded Linux operating system. But you do have an option on the 5 and 6 series to run Windows if you want to.
Right. And Ben, you missed it last week. Mike Fike showed he had a Tektronix based on Windows 2000 that had caught a virus at some point in its life. Which, cool. At some point it'll be refrigerators are catching viruses and whatnot.
No.
So, they already do, but they're the real kinds of viruses sometimes.
Right.
Anyway.
Bacteria. So, excellent. Well, again, I want to thank both of you for today. This was a lot of fun. I had a blast. From the response, people are just really thanking you both for the show here today. This is excellent.
Great. This is very cool. Thanks, Alan, and I look forward to another time when you can join us again.
Yeah, we'll get you back. And
everyone needs to make sure you check out Alan's channel again on YouTube. It's his it's his ham call sign. What is it again, Alan?
YouTube.com/W2AEW. There you go.
W2AEW.
And real quick, you have a quick story for how you got that handle so short?
The AEW are my initials.
Right.
So it's a vanity call sign. I was originally licensed in 1980 as KA2IZZ, which if you know Morse code is a lot of double dits and double das, because the letter I is double dits and a Z is two das and two dits. So it's did it da da did it da da did it. But anyway, so but then when I dropped out of the hobby for a while, came back, and I was KC2BOG, and I decided, let me get a vanity call sign, get it to be my initials, because then, when I get old and stuff's leaking out of my head, I'll still remember what my call sign is. So
or a YouTube channel. Who knew that you were making a mnemonic
Yeah, the funny thing is when I started the YouTube channel, I didn't start off thinking it's just going to be my call sign, going to be ham radio. It started off because I had a friend that had an old Tech scope, and he said, how do I use this delayed time base, this dual delayed time base? And I said, well, it's easier for me to show you rather than talk about it. So I did a little video with my phone at the time, and I said, where can I put this? I put it on YouTube, and I said, here's a link, go watch this video. And then like a week later, the video had been viewed like 100 times. Now I know my friend didn't view it 100 times. Like, wow, that's pretty cool. So since the channel was named just my call sign at that point because he was a fellow ham, I just kept it that way and just started building videos after that. So
and 19 million views later, here we are. Yeah,
here we are.
Wow.
So it doesn't have the catchy name that everybody else has. So I don't have the number of followers that like I always tell Dave Jones that I'm like minus 10 dB EEV blog, right? I'm 10 dB below EEV blog in terms of viewers, right? So.
Right.
It's not so obvious from my channel name what it is, but it is what it is.
Excellent.
But the people who need it will find you. So that's the bottom line.
Yep. So excellent. Well, I want to thank everybody again, and we will catch you next week at 2 o'clock Eastern, almost said Central, and whatever time that is in Ben's time zone. That's like 9 in the morning or 6 in the morning.
It's 11.
Or something, right? 11. There you go.
You sure it's 2 Eastern? Isn't it 1 Eastern?
Is it
That's
1?
2 Eastern.
11,
it's 2. We start at
Pacific.
1:30. Yeah, it's 2 Eastern.
It's 2 Eastern. Yeah, 11
because it's 3:30 now.
I was getting confused that you were in Mountain Time. Sorry. Yeah, 2 Eastern.
No mountains in Jersey. So,
No.
All right, we'll see everybody here next week, and you all have a good day. Alan, thank you again so much. Ben, we will see you around, my friend.
Yes.
All right.
Talking to you all.
All right, thanks.